Well, good evening, ladies and gentlemen. Some of you I've already spoken to this afternoon and earlier on for our AGM, and some of you I haven't. So for those of you who don't know me, and I've just met some people I don't know, I'm Patricia Broadfoot. I'm Chair of CPRE Gloucestershire and Vice Chair of National CPRE. And it's great to welcome you here tonight to hear from Professor Paul Bates on flooding and climate change, but more of that in a minute. I just wanted to say two things really by way of introduction. The first is that very banal, hello David, basic, which is if you feel like making a donation to CPRE Gloucestershire in recognition of the delightful tea that we've just enjoyed, Tim will be putting his hat out as you leave. So all great, it is a hat, isn't it?
It's a jar. So with this amount of hair, I can't afford to.
More importantly, I just want to remind those of you who may not be familiar with CPRE and the work we do, what we are trying to achieve. And we have this lecture, we're trying to make it an annual feature. We had one last year that some of you will have been to, where Baroness, sorry, just blocked on the lady's name. Young, Baroness Young, who's chair of the Woodland Trust, gave us a talk about trees. And that was a really very exciting and enjoyable event. None of us in CPRE want to be perceived as NIMBYs. We want to be perceived as people who are fighting our very best to protect and promote the health of our countryside across a number of different fronts, whether that's to do with fighting inappropriate development, but also fighting for the affordable houses that we need, and fighting for development to be on brownfield sites and not on our beautiful green fields, which we all know we need for growing food. And today, in fact, as I've already said earlier on, National CPRE have launched their big campaign for the next few months on encouraging the government to legislate for rooftop renewables as the first choice. That is not to make endless solar installations in our countryside, which look so awful, but actually to put them on buildings where they don't look awful at all. So that's typical of the kind of positive forward-thinking CPRE that I want to mention. And there are so many things that we as an organisation do across climate change, biodiversity, rural sustainable life, which as some of us know is very difficult with the lack of buses and so on. So there's a huge agenda that we're engaged in, and I want to thank you all for coming tonight to not only listen to an outstanding speaker, but also to support CPRE. Welcome. And I think most of us would agree that the issue of water has been very much in the media lately. And I don't know if our speaker is going to talk about sewage, but I think a lot of people have been thinking about the shocking state of the way we manage our water and drainage in this country. So this is a really excellent choice of topic, I think, for tonight. I very cheekily asked Professor Bates to give us a talk tonight because we've known each other since we were both, he still is at the University of Bristol, and I'm an emeritus professor at the University of Bristol, but I don't actually have to go to work. He does. But we both worked, Paul as director and me as a board member of the University of Bristol Cabot Institute for some years, which is dedicated to finding sustainable solutions to a lot of the world's global problems in the environment. So Paul, as the title suggests, is an expert on the science of flooding. And I've got a whole list here from his University of Bristol blurb, which says what an interesting person he is. So I'm going to read you bits of it. So you just have to stop your ears here, Paul. I expect you wrote it, so there we are. He develops simulations, models, and combines these with satellite and airborne data to advance fundamental understanding and reduce threats to life and economic losses worldwide as a result of floods. So Paul is a hydrologist by background, a fellow of the Royal Society and of the American Geophysical Union, and various other very distinguished awards, and holds CBE for services to flood risk management. What I didn't know was that he's chairman of the flood risk and analytics company called Fathom. So if you want to know about flood risks in a commercial way, then have a look at their website. So his work is on risk, resilience, uncertainty, governance, and decision-making in relation to natural hazards and global water issues. And he's published over 230 papers in international peer-reviewed journal. So what his main contribution has been is to improve the prediction of flood inundation through the development of new computer models, and as mentioned earlier, this satellite data. So Paul has worked all over the world, at Princeton, in France, in Italy, and various other parts of the world, and including working with the French National Space Agency, Brazil, as well as in Africa. So you can't wait, can you, for this lecture? And Paul, thank you so much for sparing the time for what is extremely busy schedule to come and give us a talk. So Paul's going to talk for some 400 minutes, was it? 400. 40 minutes, and there will be time for questions, I hope, if you're willing, at the end.
Yes.
So please, as we go along, do identify your questions that we can have a discussion at the end. So over to you.
Fantastic. Thank you very much. Thank you, Patricia. And thank you, everyone, for inviting me and listening this evening. I'd like to remind Patricia that actually the second time she's introduced one of my lectures, a very long time ago, as a very young junior professor, Patricia kindly introduced my inaugural lecture at the University of Bristol. So this is not quite a common occurrence, but it's not the only time this has happened. So I'll talk for about 40 minutes. Actually, we've just done some work on flooding in the UK. So we've got some sort of hot off the press information about UK flood risk, which I'm going to share with you. As Patricia said, I'll take some questions at the end, but if there's anything you've got a burning desire to just find out about, or something I don't explain well, just interrupt me. That's absolutely fine. Now, before I get going, has anyone in the room ever been flooded?
Sorry.
No, you have, and it's not a very pleasant experience, is it? Well, probably we'll have a chat about that later. But being flooded is not great. It costs a lot of money and it ruins your house. So it is to be avoided considerably. And I put this slide up first of all. This is from my hometown in Bradford-on-Avon, and it's here to remind me to say, well, flooding has been a perennial problem in the UK for very many years, and you can see from where the person took this photo that this flood level is way above human head height. Quite a dangerous level here. So we have some knowledge of floods in the past that have been very, very big. And at certain places in the country, we collect data along rivers that tell us what the river flow is at any given time. Bewdley on the Severn is one of the places where we have one of the very longest records in the UK, going back to the 1920s. And what you see here is a plot of the biggest flood that happened every year from 1920 through to, I think this goes up to kind of like mid-2010s. It's not the latest data. And the reason this is up here is just to give you an idea of the natural variability in flooding. You know, we have some years, this one here, where the flood level was about 200, up to ones a few years later where it's 600. So a 3 times range in the biggest flood in any given year. And you can see that there's kind of variability over time. And you can also see that if you are interested in what impact climate change we're having on flooding, this is the kind of data you have to work with. So it's very difficult in this to see any kind of long-term trend resulting from climate. So individual stations have to be analysed very carefully to get something out. But what you can see here, and this is also important, is that with the eye of faith, you can see that there are periods that are flood rich and flood poor. The 1960s and 70s were famously quite dry. You know, lots of people in here in the room will remember the droughts of 75 and 76. The 1940s, on the other hand, were a particularly floody episode, as were the early 1960s. And from about, well, probably about 2000 in this part of the world, we've gone into a flood-rich period again, which is still continuing. So we know we have this large natural variability. We know we have these cycles over time driven by large-scale atmospheric and ocean dynamics. And if we want to work out whether climate change is affecting these patterns, we've got a pretty serious job in order to tease that out. So what about flood risk in the UK? Well, there's about 1 in 6 properties are at risk of flooding, according to the Environment Agency, around about 5 million of them. We're spending about £1 billion a year on flood defences in the current financial period. And when floods do happen, this is Tewkesbury in summer 2007, which again, locals will remember. When floods do happen, we can get some really serious losses. Summer 2007, 55,000 homes were flooded in June and July. And that, as you know, is an awful lot of misery. Let's put it like that. 400,000 people here were temporarily without drinking water because of the Mide Bridge treatment works at Tewkesbury being near flooded. And the insurers took a bigger whack from this as well. So, how do we as scientists go about studying these things? Oh, no, okay, wrong slide. So, UK flood risk. Clearly it's driven by rainfall and our storms. This is the Met Office rainfall data over the UK. So you can see, you know, parts of the east of the country are nearly semi-arid, rainfall less than 600 millimetres a year. Out west, though, considerably wetter, you know, 3,000 millimetres a year over the Lake District, Snowdonia and the mountains of Western Scotland. And still pretty wet in this neck of the woods as well. And this all drives floods. I mean, on the exposed coasts, we get storm surges, storm waves battering the coast. This is Aberystwyth getting hit. Down in the southwest, we have small catchments that summer convective rainfall really activates. So this is a picture of the Boscastle flood that you might remember here. Elsewhere in the country, our big river systems, the downstream ends have urban areas. This is Carlisle at the bottom of the River Eden, but we have Gloucester, Worcester, Tewkesbury in this part of the world as well. And also, we've got a storm surge basin out to the east of the country. So this is an image from the 1953 coastal floods that killed about 300 people. So this is the largest peacetime loss of life in the UK. And we know that changes happen over time, but what do we know about how rainfall and river flow has changed? Well, it's not changing as fast as you might think. This is the Met Office data, don't worry about the numbers, but the headline is that the last decade, the 2010s, was about 9% wetter on average than the years from 61 to 1990. So, you know, that's a modest increase, but still more rain fell in that decade compared to in the past. And there's some natural variability, but that's also indicative of potentially a climate change trend as well. And then what does that mean for river flows? Well, this is a map from colleagues in Vienna, and they plotted change in river flows, flood flows all over Europe. You can see here in the UK, colour bar here, mostly blue. So in most places, flood flows in the UK have been increasing over the 50 years from 1960 to 2010, around about up to about 12% a decade. But there's quite a swathe in the observations over central England where flood magnitudes have actually been going down as well. So flood patterns are complex. It's not just rainfall. We also have land use changes. We have urbanization, building of impervious surfaces, building of reservoirs, the whole changes in agricultural practice, which all confound the signal. So how do we study that as scientists? Well, there are three main ways, three main data sets that we can use, two of which are interesting and only one of which actually helps us solve the problem. So we can measure things on the ground in rivers. We can put stage boards like this. We can install instrumentation next to rivers, and we can measure the water levels going up and down. We can collect water velocities, and we can calculate how much flow is going down our rivers. Secondly, we can use satellites. This is a particular radar satellite of a flood in the Belgian-Dutch border. And you can see the yellow line picks out the area we think is flooded by the satellite. That's all great, but remember that we've only had satellites for the last 20 or 30 years, and we've probably had monitoring of rivers since about the 1960s. Now, often the floods we're interested in may happen on average just once in a century, maybe even once in 1,000 years. So in most places, we've not made observations of the things that we're really interested in, really extreme floods. The only way we can really work out what those might look like is if we use computer modeling. And Patricia said very kindly that I'm a computer modeler. This is why. The only way I can make predictions about extreme floods that we might not have seen or observed is to use computer models to predict what they might look like. So you guys are all probably not computer modelers, but here's just a couple of minute introduction to how these things work. They're really quite simple. So this is schematic of a computer model and how it might work. So imagine a grid of cells. This cell in the middle has got water in it, and all the other ones are dry. Let's play the thought experiment. What's going to happen to that water if it suddenly starts to feel gravity? We've by magic got a column of water sat there. It's got to go out. A characteristic of a fluid, such as water, is it can't experience a force and remain at rest. It has to flow. So if we have a nice, if I was to turn that water upside down, I'm not proposing to, it's going to flow out in a nice concentric circle. And that's what our models do. They work out how much water is going to flow from this cell into the neighbours, and then you take the water off this amount here, and you plonk that amount into its four neighbours. And it can't just appear and disappear. If water leaves this cell, it must go into these four. So the amount that water height goes down is exactly the same amount as the water height will go up in the neighbouring four cells. Simple as that. You can't create or destroy the water. And by a bit of Newtonian physics and tracking these water volumes, we can predict how flood waves propagate over the land surface. So we tell the model how much water is coming in. So this is flow over time. We have very detailed terrain data. And some of you might have seen this. We have a technique, an aircraft-based technique called laser mapping that we use to map the land surface in incredible detail. The combination of those two things, how much water is coming in and the terrain, allows us to predict the area that's at risk of floods. And then we can always check that against these satellite images and gauge measurements to make sure that the models we build are doing a good job. So this is what they look like. This is Carlisle during the 2005 flood event that we've simulated with the computer model that my team at Bristol has built. And you can see this is the main River Eden coming in, and there's a couple of small tributaries coming in from the south. And the colour, this is overlaid on an air photo, but the colour scheme is the water depth, dark red being deep, hopefully be in line. And this model is built with a resolution of 5 meter grid cells. So it's got 5 meter spatial resolution on the ground. It can actually resolve the individual buildings here as well. So that's what our models do. And the key part about my research is being able to, instead of just doing this for one city, be able to scale up these techniques, and so I can do them over whole countries, whole continents, or even we can do this now at 30 meter resolution over the entire planet. So you're bright people, so you're not bowled over by pretty animations. Your key question here is, okay, Paul, very fancy, but does it work? So I'm going to just show you that hopefully that it does. Some of you might recognize, well, I recognize this. This is Upton-on-Severn on this island here, and this is during the November 2000 floods, which you might remember. So this is the River Severn up and downstream of Upton. And during the November 2000 floods, we were lucky enough to persuade the UK military to fly a military-grade airborne radar instrument over the flooding that was happening. And they did this for us on 4 different occasions where these vertical dashed lines are. And we built a model of this site, and we compared what our model said was flooded to what the radar said was flooded. And it's kind of a complex colour scheme, but blue is correct, and red and yellow are over and under prediction. And you can see that broadly, we get it right, and we get a very close match. So if you were the Met Office and you were predicting precipitation patterns to this kind of level of accuracy, you would be extremely pleased. Here's another one, Tewkesbury in 2007. So this is the vertical view down on the Abbey here. This is the green, muddy floodwater. So we simulated the whole of Tewkesbury at 2 meter resolution. And this is the result at the time the air photo was taken. So I'll just toggle backwards and forwards. And probably what you should do is just focus on one bit of the shoreline. So, here, or maybe this building here. This one's interesting. This building here is clearly in the air photo on a bit of dry land. They have dodged a bullet here, or been very smart about where they built. And that's the model prediction.
How old is that house?
Pardon?
How old is the house?
Well, that's a very good question. I don't know, to be honest. There's quite a lot of stuff that flooded in Tewkesbury was the more modern, on 1960s onwards buildings, wasn't it? The central core, the medieval core. I mean,
The State Drive.
yeah. I mean, you walk up from here, this side of the Abbey, and you do subtly but surely climb up quite a few meters from one side to the other.
That darker line following through the green, is that the Swillbrook just south of it?
This dark line here.
That's the River Avon up there.
Yeah.
If you drop down, there's a darker line which is deeper.
Quite probably, yeah. It'll pick up in the terrain data, so we'll flood. Yeah. So that's we can do a very good job with these data. So right. That's the kind of techniques that I use. Now, I'll go on to have a talk about the work we've done recently. This is where the kind of the interesting bit gets to. So we published a paper earlier on this year, rolling out these techniques to the whole of the UK. So we're able to make predictions of the areas at risk of flooding. And you might ask, well, why bother doing that? Surely we've got good flood risk data. And the answer is that we have some information. The UK nations, the Environment Agency in England, CPRE in Scotland, Natural Resources Wales, the Rivers Agency in Northern Ireland, all produce their own flood risk assessments, and you can type in your postcode and look up all the houses at risk of flooding. I kind of recommend that you do that. We also, the Committee on Climate Change also do these 5-yearly climate change risk assessments where they consider flooding as well. And the insurance industry also build models, which they keep rather to themselves, but they inform the insurers about how much they should be charging you for your premiums. Trouble with all of those things is that actually when you dig in as an academic, you find that there's a lack of information about how these things are actually done. There's no method information. They're not validated, and there's not much peer review. And that's kind of, that's annoying for a scientist. We also have, very kindly from the Association of British Insurers, they compile annually the amount of money they've had to shell out to pay for flood damage. The reason I mention that is when you actually compare these assessments with the ABI losses, this is the expected annual damage. So the average annual damage from government estimates is around about 2 billion, but only about 700 million if you look at the observed data from the ABI. So it's clear that not only are these things, we don't have much method information, they also seem to be overestimating the losses by a factor 3. So what did we do about that? Well, we decided actually what we needed to do was build a new UK flood model. Now, I won't dwell too much on exactly how we did it. If you're technically minded, do ask me afterwards, but it's very high resolution. It's a 25-metre resolution grid over the whole UK. So 240,000 square kilometres of land surface simulated at 25 metres. We do all flood types, obviously, and we use this high accuracy terrain that the Environment Agency and others collect. We put in all the flood defences. We have a national database about where those are, so we put those in too. And it validates pretty well against the observations. So where we checked, I'm not going to put this up, it's a bit techy and tedious, but trust me, it's not quite as good as that Tewkesbury example, but it's pretty good. Now, one thing we have to do is because floods we're interested in very rare floods. Any given year is just one random set of the floods that could have happened given the climatology. So if you really want to look at extremes, you can't just have the historic record, because that's only 40 or 50 years long, and it doesn't contain all the extreme floods that we would want it to. So instead, we build statistical models, and we simulate many thousands of years of a particular year's climate in order to get our baseline simulations. So we come up with 10,000 different synthetic 1990s, and we simulate all the flood patterns that would occur in those synthetic years. And that allows us to be much more certain about the extreme floods that we're projecting. And we've also put those into the future using the latest Met Office climate projections. And in the end, what I'm going to tell you about is how the monetary losses in the UK vary for different amounts of global warming. So spoiler alert, that's going to be the key diagram at the end.
Do you include these random tsunamis that sometimes occur?
No.
Because we had one coming up the Severn in 14 something or other, because the only bit of Brampton Church you could see was the top of the tower.
Actually, a couple of my colleagues have studied that particular
Yes.
event, and they suggest it was just an ordinary storm and not a tsunami.
Was it?
Yeah.
Mm.
But we did in 1760 have an earthquake off Lisbon, did create a small tsunami around the Cornish coast. But the 1604 event, which I think is the one that
That's it.
you're referring to,
Yeah.
is now widely thought to have just been a big storm, not a tsunami.
Must have been some storm.
Yes, it was. One of my PhD students studied it, but she found that there were larger storms before and after that were there in some of the records, but didn't gain the popular attention. It was because that one was promoted. The 1703 storm that Daniel Defoe wrote about in a book called The Storm was probably bigger. So it's which storm gets the PR.
Right. You've got to have a PR agency to work
Yeah,
with.
but the geomorphic evidence that led some people to believe it was a tsunami is quite difficult to interpret, and is quite contested. Most people don't think it was.
Right, I'll swallow it as a storm.
I'll point in the direction of the paper if you want to have a
Yes.
look. Okay, so what were our results then? There. So just remember, the Association of British Insurers say that the average annual losses due to flooding are around about 700 million. And our model, very coincidentally, quite luckily, in fact, I'd have to say, gets to within a tiny fraction of that. That's probably a bit fortuitous, as you would say. This is more realistic. So here's the Association of British Insurers data. This is expected annual damage in millions of pounds GBP. And this is a probability distribution. The insurers' data has been collected from 98 to 2018. So we've got a 20-year sample. But if you remember, I've simulated 10,000 years of flooding patterns. So what happens if I took random 20-year periods from my 10,000 years and calculated the expected annual damage from that? If I did that 10,000 times, so 10,000 times I select a random 20 years and calculate my expected annual damage, that gives me some idea of what the possible natural variation in flood losses for the UK could be. If we were to get, you know, a plausible but different set of flood events come through, the expected annual damage could be as high as 1.5 billion on average over a 20-year period, or as low as about 250. The observations sit about in the middle of this distribution, and plausibly as the average of all our 10,000 years sits exactly there as well. These dashed lines out here are the government's official assessments. This is the climate change risk assessment, and this is the Environment Agency's National Flood Risk Assessment, or NAFRA. So you can see these things, they are 3 times bigger than the mean, but that doesn't tell you the whole story. They're lying well outside the plausible distribution.
How much damage is insured? Because insurance companies are quick to run away from dangerous flood areas, and therefore they're not paying out.
So we do have some data on underinsurance. It's not very good, the data on underinsurance, but it's of the order, I get the precise number on the top of my head, but it's of the order 10 or 20% is underinsured. Insurance penetration is pretty good in the UK. The insurers do quibble about the payouts, but in terms of people who have flood insurance on their home policies, that's a pretty high percentage.
But then, I mean, a lot of people can't get flood insurance now.
Well, there is this scheme called FRS, which is designed to deal with those repeat flooding properties. So there is, at least over since the last 10 years, there is now a mechanism where the real at-risk properties can go to this government scheme called FRS. You can't get insurance through a standard Norwich Union or Aviva, but they will pass you over to FRS, and you can gain insurance through them. Whether that still applies if you're a new build in the floodplain, in which case I think it's, it's caveat emptor, isn't it? Yeah. Well, despite planning permission, properties still get built in the floodplain. Most don't, but some still do.
Can I just ask?
Yeah.
So I would expect that the national predictions are based on the models created by DEFRA and similar, or which are the basis for planning consent.
Yeah.
So they're predicting so much worst case scenario than reality.
So this is interesting. Those models that DEFRA and others use get the area of risk of flooding about right, but they miscalculate the loss that would happen if those flood events were to occur.
So they overcalculate.
Yeah, so they have the wrong exposure. So they have the wrong number of buildings there, and they have their ability to translate a flood depth into a damage is oversensitive. They say that if a flood of 1 metre deep were to occur, much more damage would happen than seems to occur in the ABI data, as far as we can tell. So the areas are right. Yeah. It's just the losses that are wrong. So when you type your postcode into the Environment Agency's website, you can have confidence that the flood map area is correct. Those seem fine. It's just the next bit of the calculation that they mess up, as far as I can tell.
Is there a plan behind this calculation?
No, I mean, it's just quite difficult to do. And it happens that, an insurer would say, well, factor 3 out is pretty good. It is quite tough to do.
Based on your modelling, are they not going to adjust the way they do their modelling?
they've had a project going on to redo all the national flood loss modelling. It started way back before the pandemic, and it's not going to deliver till 2024 or 25. So it's in train. We're hoping that this study gives them a bit of an incentive to do it better, because there's a university group out there who seems to do a better job.
Well, I can see the discussion taking off.
All right, yeah,
I think you should finish your lecture.
Let's cut to the chase then. Okay, so what happens under climate change to flood risk in the UK? So that's the key question here. So here are a number of curves, and this shows how, you know, the probability of the flood. So these are a flood here, a return period of 100, 10 to the 2 would be a flood event that happens on average once every 100 years. So these are out here, these are the losses from our 100-year events. And this is 10 years, and this is 1. And these are what are known as loss exceedance curves. This shows what's the loss in the UK from a really bad flood year. So this curve here, this dashed line, is 1990. That's our baseline for our study. It's when the world had warmed by about 0.6 of a degree Celsius above pre-industrial levels. So that's really our starting point. And what we wanted to see in our study is what happens to the losses as we go have increased levels of global warming. So as we get to 1.1 degree, 1.8, 2.5, and 3.3, what happens? Well, this is 1.1 degree. This is about where we are now. So what you can see is that between 1990 and 2020, flood losses in the UK barely changed. You know, certainly down sort of here, there is no difference. And there's a little bit difference starts to emerge from about 1 in 70 years onwards. So that's good news, isn't it? It's changed not very much at all. Climate change has not yet had a dramatic impact on flood losses. And this is one where we get to if we get to 1.8 degrees. A 1.8 degree world is what happens if all countries across the planet implement their pledges that they made at COP26. And also, all the people who've made net zero commitments, if they implement those on time and in full, we should, other scientists tell me, limit warming to about 1.8 degrees above pre-industrial. So there was a study recently that said we'd go through 1.5 degrees around about 2027 for the first time. If we do all the things that we said, we should keep to 1.8 degrees. And if we do that, the increase in flood risk here in the UK is actually quite modest. Less than 10% up at the top end, maybe about 4% taking the whole curve together. What happens then if we miss those targets? Well, if you don't do net zero and you only do COP26 pledges, you get to a world that's about 2.5 degrees warmer. And now you start to see a bit of a jump in flood losses. And if we miss the COP pledges and maybe the climate turns out to be more sensitive to CO2 emissions than we currently think, maybe you get to 3.3 degrees. That's a plausible worst case scenario. And now this is quite a leap in these losses. So how does that just numerically? This is the expected annual damage. So this is the average loss per year. And you can see that if we stick to the COP pledges, that only changes by about 4%, kind of almost in the noise. A really bad year, so a year where the losses are as bad as they've been once in a century. If we stick to the COP pledges, the increase is about 8%. We're at about 6% increase now, and it's only 8 if we meet all that. If all countries around the world meet their international commitments. If we only do the COP26 pledges or this plausible worst case scenario, the percentage change could be much higher. 20% up on the annual average, up to 40% higher in a big flood year. And in terms of engineering, less than 10% we can cope with. There's a cost, but that's kind of within the noise and uncertainty. as you get up to trying to protect yourself against 40% increases, there's a lot more investment you have to undertake. Still possible, it costs you a lot more money. The last point I'm going to make is that these are national figures. So I've taken the figures for the whole, in fact, whole GB rather than the UK. But these numbers, which are quite comforting at a national scale, do conceal a geography to this. There are distinct winners and losers here. It's not like a 4% increase uniformly. So this is the historical flood risk, where yellows are the hot spots, and you can see the hot spots are where the people are. So London, the southeast, South Wales, and Bristol. This is Exeter down here, the conurbations of the northwest, Newcastle in the northeast, and the central belt of Scotland. So that's what our risk currently looks like. It's not evenly distributed. This is the change if we keep warming to 1.8 degrees. So remember, nationally, we're hardly changing, taken as a whole. But some places are going up and some places are going down, according to our simulations. So some places, even though the national losses are manageable, some places in the country are seeing up to 25% increases in their flood losses. South Wales emerges as a particular hotspot, as does bits of the northwest and the Lake District. And there's a whole swathe of central, southwestern, northeastern England, where actually the flood losses are staying pretty flat or even going down slightly. And that's why the total loss in the country remains pretty low. But there are some losers here. And the reason for that is a complex interplay between changing rainfall patterns, changing river flow patterns, and sea level rise around the coasts. You can imagine in the future that although we're expecting more intense rainfall events, sometimes those rainfall events fall on drier soils because temperatures are also higher. So there is a trade-off between more rain, but sometimes falling on drier soils. And that's particularly the case through the central area, which is what this slide shows, but I'm going to skip over that. So let's come to the end. That is just a quick breeze through this research that we published earlier on this year, if you have a look at the paper. And it's a first complete analysis of UK flooding from all sources. And it's transparent, validated, and in the peer-reviewed literature. So there's a climate change analysis accounting for things like sea level rise and changing precipitation patterns and river flow. And the headline message here is that actually the UK flood losses are actually changed only slightly from 1990 levels so far. If you remember what I said about how rainfall and river flow were changing, 9% increase for the last decade in rainfall, flood flows in rivers are mostly up, but some places down. Our results are very consistent with those observations. So it gives us some confidence that we're kind of getting some results which are equivalent to the observations. The other take-home message here is that actually the UK needs to ensure that all countries around the world meet their climate reduction targets if we're going to keep increases in flood loss in the UK manageable. And there's a number of ways that we can do that. We need to show international leadership, we need to lead by example, but we also need to plan ahead, because we know we are going to get some degree of increase as well. That's it. Thank you very much for listening. I hope that was interesting.
Wow, thank you. It's a
Quite right.
completely masterful explanation of some really difficult data. So we'll keep you on your feet a bit longer, Paul, with questions. There's one here.
Good. Yes.
These figures that you've got for the UK are hugely detailed, really impressive. With your colleagues abroad in the southern Mediterranean dry areas, are they proportionately getting predictably drier, or what's that say about the precipitation that they can expect?
I think the broad understanding of how climate will change regionally is quite well advanced now.
Yeah.
So our computer models of the atmosphere are not perfect by any means, but they are pretty good. And we know the general shape of changes in climate in the different regions of the world. So we do know that Mediterranean countries are going to dry, probably both summer and winter. We know in the UK we're going to get warmer, drier summers, but when the rain does fall in those warm, drier summers, it's going to be more intense. And we also know we're going to get warmer, wetter winters here in the UK as well.
So more likely to get monsoon type flash floods.
I mean, I wouldn't go quite as far as monsoon type, but I would say that we can expect more intense thunderstorm convection type rainfall in drier summers in the future. That's a fairly good consensus about those regional changes in climate.
Question here.
I think you mentioned sea level rise very briefly.
Yes.
I mean, and I assume that that's actually tiny compared with rainfall.
Well,
or is it something that really, we will be aware of?
you will be aware of it. I mean, sea levels have risen about 20 centimetres since the start of the 20th century already. So that is almost detectable. These are the maps of sea level rise. This is 2030, 50 and 70. And you can see that the increase here is about 40 centimetres. So by 2070, areas of southern England are going to see increases between present day and then of about 40 centimetres. And that's the kind of the central estimate. I think that'll be noticeable. It's probably not catastrophic by that point. We can defend against a 40 centimetre increase by raising the level of flood defences at the coast. The problem with sea level rise is it doesn't stop in 2100. So even if we stick to our climate pledges, sea level rise will keep going for centuries after. So even by 2300, sea levels are going to be rising still in the UK and might not even peak and start to go down for several centuries after that. So sea level is going to get to between 1 and 2 meters above where it is presently. And it's just a question of when it's going to get there, rather than if.
Is that because of the melting ice flows?
It's because the oceans take a really long time to respond. So the oceans store an awful lot of heat, and most sea level rise is down to the fact that as the oceans warm, they expand. So every year, the Earth is hotter, the oceans absorb a bit more heat, and because the temperatures stay high, that heat absorption goes on for many decades and centuries into the future. So they continue to expand. And then, of course, ice sheets do melt.
Question here,
Yeah.
Richard.
We've had the news in the last couple of weeks about the severe flooding in northern Italy, and the comment there was that was made much worse by the prolonged drought, which had cooked the soils and indeed altered the permeability of the soils, so it all ran off. And that's something, if we get summers like last year frequently, and a prolonged drought, you're going to get worse flood events.
So in general, we understand that's the case. Do we know exactly how much those processes are going to affect flooding? I don't think we yet do, but it's certainly something that people are actively looking at the moment. So flood following drought is a serious area of active research at the moment, both here and in the US. Because remember, they've had serious droughts in California and also serious flooding there too.
Question here.
I have to consider sustainable drainage systems in my job. And obviously it's generally planning policy to implement such schemes on most new development now. In your view, if everybody correctly implemented SUDs, would it make a particular impact on the larger scale picture of what's going to happen due to climate change?
I don't think we know.
Okay.
It's a question that requires tons of local detail. But then to be able to do that at very, very large scale. So I think with the kind of setup that I described, you could run those experiments. You could say, okay, well, we know broadly what kind of impact SUDs might have. What if we implemented that nationally? Would it make a difference or not? But nobody's yet done the experiment. Yeah.
You can tell the audience what SUDs are.
Sustainable drainage systems. It's basically a way of managing rainwater, generally rainwater, over a development that replicates natural systems.
Attenuation ponds and
Exactly, yeah. And it's
Yeah.
Question, I'm sorry, go
I was
on.
going to say they're a good idea, but I don't know. We don't know very much about their net impact at scale.
I'd imagine if the oceans are going to rise, then ultimately that's going to have quite a large impact. And
Close to the coast.
managing the water on the ground alone isn't going to resolve it.
Close to the coast, the sea level rise will have a large impact. Yeah.
A question over here?
I think this is one for a social scientist or an economist, I'm afraid, but could you take your arguments further and say that when you're looking at the impact or the relative awfulness of flooding, it depends on what it's flooding, doesn't it? It's flooding a housing estate, and that's pretty bad. It's flooding 20 acres of sugar beet. It's probably not quite so.
Yeah.
I'm sure the farm would be really. It's not quite the same sort of impact, is it? Is
Yeah.
there any research going on in that sort of area?
Well, to calculate these losses, we do have to have a very high resolution map of the land use. So we have a data set which gives us information about every single building in the UK. So we know its type. And there's also a research team at Middlesex University who develop curves which, for any given building type, tell you how much loss it would incur if it were flooded. So actually there is a very, very granular analysis underneath this, down to individual building level in the UK, which works out if it's a field or if it's a two-story property, stone construction, flat roof, what its losses are going to be.
May I just say that from a purely immediate financial impact, the flood on a building can be a lot worse than flooding farmland. But in Italy, we're seeing the impact of prolonged floods on orchards and one of the most productive areas of the region, which will have an impact, will be prolonged for several decades if those trees are not going to survive it. So even though a building obviously will have consequences of a certain type, other type of landscapes may be impacted in a very different way, not less. Exactly.
So I mean, the key here is that we actually do have very detailed data on land use and buildings, so we can take those impacts into account. And in fact, that's exactly what underpins these loss curves here, is that granular analysis.
Taking the long-term sea level rise you were talking about over centuries.
Yes.
Has anybody calculated the population movement to higher land? But percentage of population?
So this, in the last couple of years, people have come up with some high resolution population projections for the UK under different socio-economic assumptions. But as far as I know, that those projections are blind to flood risk. So they do need to be redone to take that into account. So I think most people working in the field think about sea level rise out to 2100 because that's beyond the design life of most coastal flood defences and most people's lifetimes as well. But nevertheless, the fact is that sea levels do keep rising beyond that.
I mean, I would think it's going to be massive percentage of the population, because the percentage who are living, say, within 20 meters of sea level.
Well, I mean, if sea level goes up a couple of meters, then that's one set of land. If it goes up 10 metres, then you're right that you're encompassing a lot more people.
Yeah.
within
There is talk of London being flooded. Is that spurious?
I mean, we're going to have to rethink about how we defend London.
Yeah.
But early on in my career, had a day of it was a thought experiment, really. We had a role-playing game where a number of us took the roles of decision managers at different points into London's future as the sea level went up to maybe even 5 metres above where it is now. And we played all these games through the day, and I walked out of the meeting with a colleague, and we just looked around we were on the embankment, and we looked around at all the investment in London and thought, I'm never going to move this. So, for example, the Thames barrier was a response to the floods in '53. And I think eventually something more will be needed as a result. But my hunch is that
building a mega sewer, a huge pipe.
it's under construction at the moment. But that's more.
I've got a question over here, Colin.
I gained the impression, rightly or wrongly, that our government is not taking due cognizance of some of the work that you people are doing. And I say that.
That's very kind of you.
And I say that because the planning rules that exist at present, we have an allocation in each of our district areas or whatever as to how many houses shall be built in the next 20 odd years or whatever. And there seems to be no attention in that number being given adequately to the constraints of a particular district. It's true of the Forest of Dean, it must be true also of the Bristol Great Avon area, etc., etc. And the result of that is that we are, if you look at our actual constraints, there is only a fraction of that geographical landmass area upon which you can build houses. And little seems to be, or any other building, and little seems to be given to the effects of climate change and the effects of flooding. In my own parish, by 2050, about a third of the parish is going to experience flooding, every X years, whatever it may be, 10, 100 years, whatever it may be, certainly within the lifetimes of the buildings which they're talking about putting on that land. So, am I correct?
Well, you are. I mean, I'm not an expert on the planning system, but I do know that despite the best efforts of actors in the planning system, houses still get built in flood-prone areas. And it seems to me crazy that you continue to store up risk for yourself by doing so. The easiest thing we can do to protect ourselves against flood risk is not build in harm's way.
Is there the degree of concretization, as in building, is that adding to the risk?
In small catchments, yes. So paving impervious surfaces, quicker runoff, more runoff will change that. Over a big catchment like the Severn, it's very difficult to see the effect. But over a small urban catchment that used to be undeveloped and is now urbanised, you will see distinct changes in runoff.
One more question, anybody? Oh, yes. Please.
Have you got your map showing each building?
Yes.
Is it possible from your map to know the period those buildings were built? So were our forefathers more intelligent about where
or did they just knock down everything that got flooded?
I live in a building that will get 1300, where we will get flooding all around, but never ever in our building.
Yeah.
Just doesn't.
So I've thought about this a little bit. Well, there is some information in the data sets we use on age of construction, but I wouldn't necessarily rely on it past 1600. So Is it because our forebears were smarter? Did they have more choice about where they could build? For example, it's fairly obvious if you're going to build a house in a low-lying bit of the country that you might pick something that is on a slight raise, you know, like Ely in the Fens, or indeed Upton. Or did they? Or is it just the fact that the only thing that survived survives are the things that were fortunate enough to be in the right place? So all the buildings around there, which were built on the low bits, and they thought, oh well, we'll knock that down. So the answer is we don't really know, but it is interesting when you see the photograph of Tewkesbury Abbey and think, somebody knew what they were doing there, surely.
Yeah, it's very nice.
There is a flood mark in the one of the entrances to Tewkesbury Abbey, so it's not wholly new.
Well, I think the time has come, Paul, for more informal chat over a drink outside. So I'll call on one of our vice presidents, Professor Adrian Phillips, to give a vote of thanks, please. Yes.
Well, when you started, you asked us, did anyone directly affected by flood? As far as I could see, only about 2 hands went up. My father was affected because in his care home was flooded, and my son's home was flooded. And it just made me think that it's not only about money, it's also about the kind of misery. An appalling view of my father's home, his room in his home care after it's been flooded was most appalling.
Yeah.
Anyhow, I think one of the biggest problems we have at the moment is to make the science intelligible to the decision makers and also to us, the public. And what I think you've done today is to do that extremely well.
Thank you.
I'm sure that what you have come up with will have some influence upon government and probably certainly on their advisors. And it should help inform us as the public who are going to have to live with the consequences of decisions that might be made around climate change, help us be better informed too. So thank you very much for a really interesting, enlightening and extremely thorough presentation. Thank you very much.
Thank you very much.
The inaugural lecture was quite good too.
Good to know I've not lost my touch.
Everybody, there are drinks and nibbles which we've had moved from this humdrum building onto the beautiful grass outside. So please do stay and enjoy some fellowship with each other and with our speaker. And if you feel like it, make a donation. Thank you.